Thank you for sticking around. If you're here because of a delayed flight, though, I'm sorry. Better luck next time. So I'm going to talk about work that I've been doing with these very fine people on ancient glacial deposits. And so this is an example of a glacial sequence in Ontario. This is from the Paleoproterozoic. Here you have a drop stone in these laminated argillites. So this is basically something that was probably dropped by a melting iceberg in a shallow continental margin type environment. So we're interested in basically three questions. First is, what is the average composition of the Earth's upper continental crust? And this is particularly important in geochemistry in terms of just understanding the whole Earth because of the fact that the upper continental crust in particular, well, the whole continental crust, but particularly the upper portion, it exerts a very sort of disproportionate leverage on the budget of many important trace elements compared to its relative mass and volume relative to the rest of the Earth. And if you're trying to figure out how the Earth differentiated from some largely molten, very hot ball in the beginning that was homogeneous to what we have today, you need to know a sort of an end member of what we have today and how it's changed through time. So the other question we are looking at is how has the composition of the upper continental crust evolved through time? And also, we're looking at how the effect possibly of the rise of oxygen through the Earth's history, both in the hydrosphere and the atmosphere, has affected the composition of the upper continental crust. So the approach here is to look at ancient glacial diamictites or tillites of different ages to sort of come up with a time compositional portrait of the Earth's upper continental crust. So this is an approach that's broadly inspired by Goldschmidt. He actually suggested looking at glacial loess and glacial outwashed loams from the Pleistocene and the early Holocene to look at sort of the modern composition of the upper continental crust. We're applying this approach going back in time through a series of periods where we had large ice sheets in the Earth's history. So the advantages of using till or tillite or dimictite glacial origin as a UCC proxy compared to things like shale, which are commonly used for this purpose, obviously if you have a continental ice sheet like what's on Greenland or Antarctica, these ice sheets are sampling very large areas of crust and dumping that material at some final destination offshore. The weathering process is primarily physical rather than chemical, so you're not having as much fractionation of elements due to dissolution of phases, or incongruent breakdown of minerals chemically. And also, just by definition, till or tillite has limited particle sorting by hydrodynamic properties. And that's another thing that happens with types of sediments like loess that's windblown. You have enrichments in certain minerals that affect the chemistry of the bulk material that you're analyzing. So we're looking at samples from 4 different periods broadly in the Earth's history where there were major ice ages prior to the Cenozoic, obviously. In the Paleozoic, there was a very large ice sheet in the southern hemisphere on Gondwana, supercontinent. We have samples from 2 places in Gondwana. The Neoproterozoic was the period of the famous snowball Earth glaciation or glaciations. The Earth may have been completely encased in ice, or it may have been just very, very cold with lots of ice. That's still pretty controversial. And there were really 3 different intervals, 3 different separate glacial events that most people consider during that interval. And we have samples from a very large number of different places in the modern world. The Paleoproterozoic, the very beginning of the Proterozoic, was perhaps an equally severe glaciation compared to the Neoproterozoic, but because it's much further back in time, the geological record is a bit thinner. But in any case, you have deposits from a lot of different modern continents that have been recognized. Ours are from 2 different modern continents, Africa and North America. And another thing to point out about this interval is that this is the interval of the Great Oxidation Event, where for the first time in Earth's history, as far as we can tell, oxygen in the atmosphere rose above about 20 parts per million. For any length of time. And then there are dimictites from the Mesoarchean, about 2.9, and the Pongola supergroup in South Africa we've sampled. And the plots that I'll be showing use this age-based color code, by the way. So this is just an example of tillites in their natural habitat. This is in Ontario, the Huronian supergroup. This is the Bruce Formation. And so just to clarify here, we're interested in the matrix material. So tillites, they obviously contain all these different classes of different sizes. But we're basically taking big bags of this stuff back to the lab, crushing it up into chips, and then we're picking out the clasts, and then crushing up just the matrix material, so the fine grain fraction. And that is what we're analyzing here. So the methods are, we're just doing ICP-MS trace element work, and we're also preparing composite samples, so basically composite powders that represent mechanical mixtures of a large different number of individual samples from a given stratigraphic unit for a given age and location. And these are things that we basically made as sort of something on the same lines as POS and NASC, the famous composite shales that have been made available to the whole community for looking at crustal evolution and average compositional parameters of the crust. So these are things that we've made to be available to the whole community if you're interested in looking at the next isotope next isotopic flavor of the year on these. And we also have oxygen isotope data on the whole rock material. So just to sort of provide details of how the whole system with the composites work, this is a trace element variation diagram. You have elements listed in order of their increasing compatibility from nickel all the way to cesium. These are normalized to the Rudnick and Gal model for the UCC, the upper continental crust. The blue field here represents the whole range of variation for individual samples from these two formations of Neoproterozoic age in South China. And you can see here that it's not a huge variation considering the number of samples and the fact that we have two different units of different ages. One is about 640 and one is about probably 700 MA. And the solid lines and boxes represent the composites for this unit and that unit. So you can see that they fall very well within the sort of the middle of the range of the full variation for the individual samples. And I'm going to actually just show the composites for the rest of the talk for the most part as basically a way of sort of cutting to the average values that we have for a given unit and locality. So I'm going to show a series of plots that look at sort of the time versus compositional parameters. I guess that's kind of cut off. So that is nickel versus aluminum times 1,000. So basically nickel is a very compatible element. It's present in mafic minerals and mafic rock types, enriched in those types of rocks. Aluminum is something that doesn't vary a whole lot in sedimentary systems, so it's basically a normalizing factor to eliminate the effects of quartz dilution. And the main point here is that you see this, you see dramatically more mafic crustal material in the Archean. You see this sort of step change at the Archean Proterozoic boundary, and then sort of a further decline going up to the Phanerozoic. And you might look at this one point here and say, wonder what's the deal with that. So that's actually the Dwika formation, or the Dwika group in South Africa, which is deposited at about 300 million years ago. This group of samples comes from a portion of that basin where the provenance based on detrital zircons is entirely pre-2.0 GA. So all of the detrital zircons in this group of samples represented by that composite are greater than 2 billion years old. So basically, this is just the signature from stuff this age without any more modern crust involved. Now, another parameter commonly used in studies of sediments for looking at sort of mafic versus felsic contributions is the thorium scandium ratio. That's thorium there, scandium. Thorium is something that increases with differentiation, and it becomes concentrated in more felsic materials. Scandium does sort of the opposite. And again, you can see that you have more mafic materials basically based on the lower ratio in the Archean, and this sort of increases through time towards more felsic compositions. The europium anomaly, so that's europium star, or europium versus europium star divided by europium star. So this is basically on a rare earth pattern how much europium is depleted relative to the other neighboring rare earth elements. And this is something, again, that the europium anomaly becomes more negative. The value becomes lower with increasing differentiation, particularly when plagioclase or K-feldspar are involved in fractionation. So you can see basically that you have an increase in the magnitude of the negative nature of the anomaly through time, which further is evidence for increasingly felsic and differentiated crust through time. So all of these basically say the same thing that work on shales have shown, that basically shales, people looking at shales for this same purpose have found that the crust is becoming, it's become more felsic and differentiated with time. So it basically demonstrates that the tillites can be faithful recorders of the average composition of the Earth's upper continental crust. Another ratio that's of critical importance in understanding the Earth, which is, I guess, is cut off again, is the thorium-uranium ratio. Those are both very important elements because they're primary producers of heat in the Earth. They're basically the two most important elements for driving mantle convection. Understanding how much of that heat-producing budget is within the crust versus the mantle is very important for understanding how the Earth has evolved through time. So these are elements that generally behave similar to one another during igneous differentiation, but there are other processes that can mobilize one of these elements. So you can see here that there's a fair amount of scatter, but there's a broad increase through time with decreasing age in the thorium-uranium ratio. And obviously these are the things that produce different isotopes of lead, so understanding the lead isotopic evolution of the Earth that goes hand in hand with this ratio. So we think that the decrease in the ratio through time is due to the loss of uranium due to the oxidative mobilization of uranium. So uranium is insoluble under anoxic conditions, but it becomes soluble because it switches from 4+ to 6+ when you have significant amount of oxygen around. And then it'll just go into solution, and it'll get washed into the oceans and maybe recycled back into the mantle. And in fact, if you look at mantle-derived basalts through time, as many other people have done, you see a pattern that basically goes like this. So the mantle shows the complementary pattern to the crust as we would hope it would. And further pointing at the theme of the effects of oxygen and the changes in the amount of oxygen in the Earth's atmosphere and hydrosphere through time, molybdenum is a very redox-sensitive element. This ratio is basically just an enrichment factor or depletion factor for molybdenum. So it's depleted relative to insoluble elements of similar compatibility if it's less than 1, or it's enriched if it's greater than 1. And we see that there's this abrupt change in the amount of molybdenum relative to similar elements after the Great Oxidation Event, so after the Paleoproterozoic glaciation. So we go from this variable but sometimes enriched values to these generally depleted values in the Neoproterozoic and the Paleozoic when we had a lot more oxygen around, which makes perfect sense. So basically, the crust is losing molybdenum to the ocean basins. And if you look at black shales, as many people have done, they show the exact opposite pattern in their molybdenum abundance. So they basically go like this. And then interestingly, we looked at oxygen isotopes in the powders. And oxygen is basically an indicator of interaction with the Earth's hydrosphere. So the mantle has a value of about between 5 and 6. But the Earth, the oceans, so interaction with hydrosphere, low temperature interactions between water and rock cause values to go up. So you notice that in the beginning of our record here for the tillites, we have values that are close to the mantle value, but they increase through time. So the question is, what is causing this? And by the way, the ones that are open circles are ones that are rich in carbonate. Carbonate has a very high oxygen isotope value compared to silicate materials. So that is going to obviously affect those results. But anyway, the causes are for this pattern that we see. There are a couple of different possibilities. One is that we have greater recycling of older sediments into these new sediments with time. And if we look at indices for sedimentary recycling like zirconium, scandium, which generally goes up when you recycle old sediments, there's sort of a general correlation between the delta O18 values and this ratio, which suggests that sedimentary recycling is definitely a factor here at play. But also, if you look at the changes in the actual infrastructure of the Earth's continents through time, so the basement, the granitic rocks and the metamorphic rocks, they show the same pattern in oxygen isotopes in zircon, which is pretty much, that's almost impossible to alter. So we basically think it's a combination of this recycling factor and the fact that the actual sort of crystalline crust is changing in composition also. So just to conclude the main points here, we think that the tillites are providing faithful records of the secular evolution of the UCC. The UCC has become more felsic and fractionated with time, and we see the effects of oxidative weathering on the bulk composition of the UCC, particularly after the great oxidation event at 2.3-ish. So thank you.
Any question for it?
So we actually have tetraedral zircon data on a number of these samples. What? Oh, sorry. So we have tetraedral zircons on a number of these samples. And we also, I've started doing common lead isotopes, more to get at the question of how the kappa values have changed through time, getting at the thorium-uranium ratio again. But if you look at the tetraedral zircons, for the most part, the components that are going into the tillites are decreasing in age with the age of the tillites. So that's sort of that one case that I mentioned is sort of an anomaly where we don't have any young material in the tillite. It just goes straight from, from the 300 MA deposition age to the youngest zircon, which is 2.0. Yeah, so we have that information, and it's generally less than shales, but it's higher than primary igneous rocks. So the idea that there's going to be no chemical weathering during glacial processes, it's not totally true based on these data. You might have seen Roberta's talk on the same subject matter. So there's the values are, I would say, on average of about, say, 65 for the CIA, but the values are higher in the Archean, which is interesting. You may have had just a more aggressive atmospheric chemical weathering regime. Yeah. Sure. Yeah. Oh, yeah, that paper, yeah.
The thorium uranium ratio is high and very low.
Yeah.
When you go to the young crust, the thorium uranium ratio is low with little variation. So it's exactly the opposite of what you see. So how can we understand it?
Well, no, I think actually and this is based on sort of my preliminary interpretation of the lead isotope data that I have, is that the loss of uranium is actually something it's an artifact of the crust that's being weathered, as Roberta implied for the issue of the CIAs. So, yeah. Did I answer your question?
She's saying that modern river sediments old crust.
Oh, that's just because they've been exposed to the atmosphere and to the hydrosphere for a much longer time, presumably, than a young orogeny. Well, it's again, it probably goes to the fact of greater sedimentary recycling through time. You're producing more and more crust that has a greater proportion of sediments as its makeup, is perhaps the thing. Yeah. So So the last talk is by Ilya Bendeman.